Welcome to The Explainer. Today, we're taking textbook physics and, well, making it completely visible. We're going to explore those incredible invisible laws that govern literally everything around us, from the shifting weather patterns in our atmosphere to the mechanics of airplane flight and even the blood pumping through your veins right now. We're talking about the mechanical properties of fluids.
Okay, let's dive into this. Here's our roadmap for today. We'll cover what is a fluid, the power of pressure, understanding fluids in motion, Bernoulli's principle in action, viscosity and fluid friction, and finally, the magic of surface tension.
Section 1. What is a fluid? Defining the basics.
So I want to pose this question directly to you. What exactly is a fluid? If you're like most people, your brain probably just pictured water, right? Or maybe a cup of coffee. But in physics, we kind of need to challenge that everyday assumption because fluids aren't just liquids, they are also gases. The air filling the room you're sitting in right now, that is a fluid. But, what actually unites a heavy liquid and a nearly weightless gas? Well, it all comes down to shear stress. See, a solid has a definite shape, and it highly resists what we call shear stress. Basically, forces that try to slide its layers past one another. Fluids, on the other hand, well, they have no definite shape of their own. They yield to incredibly small amounts of shear stress. In fact, to put it into perspective, a fluid's resistance to shearing is about 1,000,000 times smaller than a solid's. That total lack of resistance is the fundamental property that allows them to just flow and take the shape of whatever container you put them in.
Section 2. The power of pressure. Static fluid forces.
To really understand static fluids, we've got to understand pressure. By definition, pressure is the normal force acting per unit area. Let's use a pretty visceral analogy from the textbook to make this stick. Imagine an elephant stepping on a man's chest. Yeah, his ribs would absolutely crack, right? But you've probably seen a circus performer safely lying down on a bed of nails, sometimes even with a heavy wooden plank right on top of him. So why does the performer survive? It's all about the coverage area. The smaller the area a force acts on, the greater the impact. Pressure is literally just about how widely that force is distributed. Now, while liquids and gases are both fluids, they handle that pressure very differently. Liquids have a much lower compressibility. Their density varies very little, even under wide pressure and temperature ranges, so we generally treat them as incompressible. They basically maintain a fixed volume. Gases, however, are highly compressible. Squeeze a gas and it's going to exhibit massive variations in density, shrinking down to fit a tight space or expanding out to fill its container completely. And this brilliantly illustrates one of the absolutely crucial rules of static fluids, Pascal's law. Look at this right-angled prism, which represents a small element of fluid at rest. Pascal's law dictates that, if we ignore gravity, the pressure is exactly the same at all points within a fluid at rest. Plus, the fluid exerts a force on any submerged surface, and that force is always normal, meaning exactly perpendicular to the surface. Think about it. If it weren't perpendicular, the fluid would start to flow, and, well, it wouldn't be at rest anymore. So why does Pascal's law actually matter to us? Because it's the secret behind everyday mechanical miracles. Imagine two syringes of different sizes connected by a water-filled tube. If you apply a small, say 10 Newton force to a small piston, maybe 1 centimeter in diameter, that pressure transmits equally through the entire fluid. When that exact same pressure hits a larger piston, like 3 centimeters in diameter, it exerts a massively amplified upward force. This is the exact principle behind the hydraulic lifts that raise heavy cars at your local mechanic and the hydraulic brakes that safely stop your car every day.
Section 3. Understanding fluids in motion. Equation of continuity.
Okay, let's get things moving. Imagine water flowing steadily through a pipe that suddenly gets narrower. What happens? We rely on what's called the equation of continuity. It states that for an incompressible fluid, the area of the pipe multiplied by the velocity of the fluid remains absolutely constant. Because mass is conserved, you can't just lose water halfway through the pipe. The volume flux has to remain strictly constant. Therefore, when the pipe narrows and the area decreases, the fluid has absolutely no choice but to travel much faster just to get the same amount of mass through in the same amount of time.
Section 4. Bernoulli's principle in action. Conservation of energy.
Back in 1738, the Swiss physicist Daniel Bernoulli developed a relationship that literally changed the world. He showed that fluid flow is really just a complex balancing act of energy. So the crucial point is, for a steadily flowing incompressible fluid, 3 things are constantly being traded back and forth: the pressure of the fluid, its velocity or kinetic energy, and its elevation or potential energy.
If a fluid speeds up, its internal pressure must drop. If it slows down, its pressure increases. It is a perfect, elegant conservation of energy.
Now, you might be wondering, okay, that's a nice mathematical equation, but how does this actually apply to real life? Well, let me show you the practical magic of fluid dynamics. Look at this incredible example. A fully loaded Boeing aircraft has a mass of 330,000 kilograms, and it flies level at 960 kilometers per hour. How on earth does something that heavy stay in the sky? Because of its wings and Bernoulli's principle. The wings are shaped so that air travels faster over the top than the bottom. Faster moving air means lower pressure on top. This creates a massive pressure difference across the 500 square meter wing area, generating a tremendous upward force we call lift. Bernoulli's principle is literally lifting hundreds of thousands of kilograms into the air. No way, right?
Let's look at another amazing application of Bernoulli's equation, Torricelli's law. It describes the speed of efflux, which is just a fancy word for fluid outflow, from a hole in the side of an open tank. Through Bernoulli's math, Evangelista Torricelli discovered something wild. The speed of the liquid shooting out of that hole is mathematically identical to the speed of a solid body freely falling through the air from the exact same height as the water level. The fluid is essentially falling out of the tank.
Section 5. Viscosity and fluid friction. Internal resistance.
Now let's slow things down a bit. Viscosity is basically the friction that occurs within the fluid itself as its layers slide past one another. And here is a deeply relatable fact right from the textbook. Blood is visibly thicker or more viscous than water. But what's truly amazing about human biology is that the relative viscosity of your blood, compared to water, remains perfectly constant between 0 degrees Celsius and your normal body temperature of 37 degrees Celsius. It's a remarkable property that makes sure our circulatory system functions smoothly, regardless of normal temperature variations.
Section 6. Magic of surface tension. The elastic skin.
Let's move to the final piece of the puzzle and see how this builds at a molecular level. Deep inside a liquid, a molecule is surrounded by neighbors and gets pulled equally in all directions. But the molecules right on the surface, they lack neighbors above them. This creates a net inward pull, pulling the surface molecules tightly together. This phenomenon creates what we call surface energy, making the surface act like a stretched elastic skin. This is exactly why you have to blow a little extra hard to form a soap bubble. You physically need extra air pressure on the inside to overcome the elastic surface tension pushing inward.
This elastic surface skin also creates a pretty weird phenomenon called capillary rise. Because of the pressure difference across the curved surface where water meets air, water can actually be drawn up into a narrow tube, completely defying gravity. Fun fact, the Latin word capilla means hair. If the tube is as thin as a human hair, this capillary rise would be incredibly high. It's the exact same principle that allows giant trees to pull water from their roots all the way up to their highest leaves.
I want to end this explainer with a really provocative thought exercise, pulled right out of the chapter's problem set. Think about this for a second. Why do fast jets of water gush out aggressively when you try to partially close a running water tap with your fingers? Well, the answer lies in that equation of continuity we discussed earlier. By blocking the tap, you dramatically reduce the area the water can flow through. Because the same amount of water mass must still escape, it has to accelerate to a super high velocity to get out, creating those high-speed jets. It's textbook physics happening right there in your kitchen sink. I really hope this explainer leaves you eager to look at the everyday world through the eyes of a physicist. Thanks for joining me on The Explainer.